Hello, welcome to the channel of Namagiri Academy. In this lecture, we shall talk about the integration, double integration over the regions that are not rectangular. So let us uh, begin with an example. Let us have a region which is defined, so let R be defined mm, as bounded between the lines x equal to 0. So this is y axis, y equal to 0, so this is x axis, and x plus y equal to 1. So to draw the figure, it is something like this. It is in the first quadrant. This is y axis, this is x axis, and if this is y equal to 1 and this is x equal to 1, then the line connecting the two is x plus y equal to 1, and it is this region that we want to integrate a certain function. Which function do we want to integrate? F of x y. So we want to compute uh, e to the power, let's say, 2x plus 3y over r, where this is r, dA. So in the previous lecture we saw how to integrate such functions over r when r was a rectangle, and we did it using Fubini's theorem, which tells us that over a rectangle r, this such integrals can be integrated computed using iterated integrals. That technique, so we shall use the same technique, but now the region of integration is not rectangular, and therefore the where will the difference show up? It will be in the limits of integration. We want to compute this. Okay, now this is 0, this is x equal to 1, x equal to 1, this is 0, this is y equal. So now pay attention, how are we going to define um, between which two values x will vary and between which two values y will vary. Earlier we saw that when R is a rectangle which is AB cross CD, any rectangle in plane has this form, and in that case x varies from A to B. So therefore we have A less than or equal to x less than or equal to B, and C less than or equal to y less than or equal to D. And writing region in this form, as I remarked in the previous lecture, writing the values of x in terms of inequalities is often useful, and that casts some light on the limits of integration, and that will that will be demonstrated in this case, how writing um, inequalities comes in handy. So when we have rectangles, we have set these inequalities, and in that case we simply integrate function f of xy in this fashion. There is no um, complication in such cases, okay, because all a b c d are constants. But here the situation is a little complicated. X is varying from 0 to 1, but y is also varying, as such varying from 0 to 1, but not for every x. Now let's try to understand. Let's try to um, uh, figure out the limits of integration of x and y. So first um, we shall begin by um, uh, letting x vary from 0 to 1, and then accordingly see for a fixed x how y varies. So suppose this is x here, okay. Now y varies for this x from this point to this point, we if we want to remain inside this region, okay. So this is y equal to 0 because this point lies on the x-axis. And what is this value? uh, this is 1 minus x. Okay, so for every point when x varies from 0 to 1, for every x, y will vary from 0 to 1 minus x. Here 0 to 1 minus x. When x will be 1, y will be from 0 to 0, as you can see over here it is just 1 point, so therefore that is verified. And when x is equal to 0, y will vary from 0 to 1, as you can see over here it takes its full range. So this helps us setting the limits of integration. So when we are dealing with general regions, the most important thing is to set the limit of integration, which can be done by drawing the diagram, drawing the region, and then seeing for a fixed x between which two values y varies. Okay, so now given this, how are we going to compute the integral, this integral region x e to the power 2x plus 3y dA. Now we can use iterated integrals. This was iterated integral in case of the rectangle. Here also we shall use iterated integrals, but now the limits will be different. The limit of x is 0 to 1 and limit of y is 0 to 1 minus x. Mind well the order of integration. Here we are integrating with respect to y first, and therefore it is dy, and then outer integral is with respect to x, so its limits are 0 to 1. Okay, fine. Now what? Nothing else. So now we continue in the same way. Here we have e to the power of 2x plus 3y, so that can be written as 1 minus x e to the power 2x multiplied by e to the power 3y dy dx. Now e to the power 2x is constant with respect to y, so we can take it outside. So or we can keep it as it is, and e to the power 3y, the integral of that is e to the power 3y divided by 3. Now we have to substitute the limits of integration. Now the limits of integration are in terms of x. Earlier the limit of integrations were in terms of they were constants when it was a rectangular region. Now let's substitute here. Now again, don't confuse between this and this x. This x is constant here. This x is the limit of integration for y, so therefore we shall substitute for y over here in terms of x. So e to the power 2x as it is, e to the power 3 times 1 minus x over 3 minus e to the power 2x multiplied by e to the power 0, which is 1 over 3. And this with integrating this with respect to x. Okay, 0 to 1. So now this is fine. This will be like e to the power 2x multiplied by e to the power 3 multiplied by e to the power minus negative 3x minus e to the power 2x divided by 3 dx. So e cube e power minus 1 e to the power minus x minus e to the power 2x divided by 3 dx. E cube so this is the derivative of integration of this is e cube over 3 multiplied by to the power negative x divided by negative 1 minus the integration of this is e to the power 2x divided by 2, and this 3 remains, so 6. Sorry, so I shouldn't write here integral sign. And now substitute the limits of integration. Alright, so here e cube multiplied by e to the power negative 1, so that is e square. So it is e square divided by negative 3 minus e square divided by 6 minus, now we shall substitute 0, so e cube over negative 3 minus 1 over 6. So whatever it is, whatever is the value, and compute for yourself. So the whole point of uh, this example is to show how to find the limits of integration when the um, region is not rectangular. Now I would like to demonstrate something else. um, the region of integration that we had was this. X equal to 1 and y equal to 1, and for every x we realized that y varies from 0 to 1 minus x, x plus y equal to 1. But now this can be alternatively thought in this manner. We can let y vary freely. Y varies freely from 0 to 1, and let's see what happens to the value of x for every y. So suppose this is y, then what are here, x varies horizontally, right? Y varies vertical. So what are the what between which two values does x vary for every fixed y? If this is fixed y, then x varies from 0 to, what is this? This is 1 minus y. This value is 1 if this is y, then this is 1 minus y. You can because this is a point on the line x plus y equal to 1, so x is equal to 1 minus y. So this segment, all the x coordinates on this segment satisfy this 0 less than or equal to x less than or equal to 1 minus y. All right. So we can compute this integral by uh, first letting y freely and letting x to move between 0 and 1 minus y. Now the answer certainly will not change. Now first we are integrating with respect to x, and let us see what we get. Now with respect to x, y is constant, so e to the power 3y, e to the power 2x over 2, 0 to 1 minus y dy. E to the power 3y, e to the power 1 minus 2 times 1 minus y divided by 2 minus e to the power 3y multiplied by 1 over 2, so 2. Okay, d. Let's see what we get. E to the power 3y multiplied by e square multiplied by e to the power y over 2 minus e power 3y over 2 dy. Let us compute this. This is e square e power y over 2 minus e power 3y over 6 from 0 to 1. So this is e square. Let us substitute y equal to 1 first. E square multiplied by e to the power 1, which is e cube, that gives us e cube divided by 2 minus e to the power 3 multiplied by 1, so divided by 6, minus, now substitute 0, so this is 1 e square divided by 2 minus 1 over 6. Now we may have to check what is happening over here. Possibly the answers, we expect the answers to be same because we are integrating the same function over the same region as we did before, only that we have changed the order of integration. This is called as the changing the order of integration. Earlier we integrated with respect to y first and then we integrated with respect to x. Here we are integrating with respect to x first and then we integrated with respect to y. That depends on what view we take of the region, whether we let x change freely and restrict y according to how x change, or whether we let y change freely and restrict the limit of x accordingly how y varies. Okay, so now suppose this is how to compute this 3 times this, so 3 minus 3 e cube minus e cube divide, so 2 e cube divided by 6, so e cube over 3 minus e square over 2 plus 1 over 6. That is our answer over here. Let's check whether this is the same thing over here. E cube over 3 plus e cube over 3 is correct. E cube over 3 minus here it is 2 times e square minus 6, so minus 3 e square over 6, so minus e square over 2 minus minus plus, so plus 1 over 6 is, so verified. So the answers are equal. So now that tells us that how to, so this has verified, so this then tells us how to compute first very basic demonstration of how to compute the double integral over general region. Let us take one more example, and this also has served as an example of how to change the order of integration. We shall discuss the change of order of integration in greater detail in the coming lectures, but this is the first demonstration. Let us take one more example. Let R be the region bounded between y equal to x, y equal to root x. Okay, so here there are no limits given for x, but we are given these two conditions. They may be sufficient, and we may have to draw a diagram to see whether that is sufficient or not. Com- compute, let me write the function that we want to compute. X square plus okay, so now let us draw the line y equal, this is the line y equal to x that passes through the origin and makes slope has slope equal to 1, and y equal to root x is the same as x equal to y square, so it's a parabolic thing. It's a parabola of this sort, and they will exactly intersect at x equal to 1. Observe that when x is equal to 1, y is also equal to 1. So this, on this line, this point 1 comma 1 lies on this line, and also this point 1 comma 1 lies on this curve y equal to square root of x, because when y equal to 1, square root of 1 is 1, which is x equal to 1. So therefore this 1 comma 1 lies on both these curves, this line as well as this curve. So we want to compute this integral in this region, all right, good. Now what should we do? We shall apply our um, previous technique. All that we want to do is to let x move from 0 to 1 and see between which two values y varies. So this x square plus y square integral of that dA. Now let x vary from 0 to 1, and between which two values does y vary for every x. So if x is here, then within this region y varies from this point to this point. Now this point corresponds to y equal to x, because this is the line y equal to x. Okay, so we shall go from lower limit to upper limit, and this point corresponds to square root of x, because this is the curve y equal to square root of x, and this is the line y equal to x. So for x, y is moving from x to square root of x. Don't write it as from square root of x to x. We don't want to come downward. We always go from lower value to upper value while taking definite integrals. Okay. Now we have changed this into iterated integrals. X square plus y square. These limits are for y. So first we shall integrate with respect to y, and then with respect to x. Now our job is much simplified. X square is a constant with respect to y, so its integral will be x square y, and integral of y square is y cube over 3. limits of integration and then dx. So 0 to 1, let's substitute for y x square root x. So it is x to the power 5 over 2 plus um, root x cube. So x to the power 3 over 2 divided by 3 minus x cube minus x cube over 3 dx. Now we have got a function in x alone and we have to integrate that. So x to the power 5 over 2, the integral of that is x to the power 7 over 2 divided by 7 over 2, so that is 2 over 7 plus x power 3 over 2 over 3 that is x power 5 over 2 multiplied by divided by 2 5 over 2, that is 2 over 5, and this remains as 3 as it is, so 50. Now this minus x cube over 3 together becomes negative of 4x cube over 3, and the integral of that is negative of 4x to the power 4 divided by 4 multiplied by 3. So the 4 gets cancelled, so x power 4 over 3. And now we shall substitute the so since the lower limit is 0, everything will become 0. The upper limit is 1, so that is 2 over 7 plus 1 over 50 minus 1 over 3. So we may have to compute that. That is now here. Let me leave it as it is at present. Here again I would like to demonstrate how to change the order of integration. Here we are first let x vary from 0 to 1, and accordingly for every x we allowed y to vary from x to square root of x. Now what happens if we reverse our view, if we allow y to vary from 0 to 1 and see for for every y how between which two values x should vary to give us the same region. Let us redraw the diagram. I'm sorry, not a very good diagram, but please bear with me. This is x equal to y, and this is y equal to square root of x, which can be equivalently written as x equal to y square. Okay, this is y equal to. Now suppose y will let y to vary between 0 and 1. What are the value for every y, fixed y, Between which two values does x vary? It varies from this to this. Okay, from lower to higher. This is this point lies on the curve x equal to y square. So x varies between y square and y, because this point lies on the line y equal to x. Okay, so we can take the other view of the same integral. We can compute this x square plus y square by uh, integrating with respect to x first, where the limits of integration with respect to x are a y square and y, and then with respect to and then integrating with respect to y. So fine. So what should we do now? This is uh, what is the integral with respect to x? So x cube over 3 plus x y square from y square to 1 dy. Okay, now we shall substitute here the values of the functions of y for x. Y square will remain as it is. Only the expression, only the x will be replaced by 1. So x cube, here first it is y cube over 3 plus y cube minus y power 6 divided by 3 plus y to the power 4 dy. Okay, so this is 4y cube over 3, this part. So we can just directly integrate 4y cube over 3 here. This, the integral of that is y over 4 over 3 minus y to the power 7 over 7 and then 3 y to the power 7, so 21 plus y power 5 over here it should be negative. Zero to 1. Here again, when we substitute the lower limit 0, everything will become 0, and the upper limit is 1. So after substituting, it becomes 1 over 3 minus 1 over 21 minus 1 over 5. Let us try to compute this. This is 7. If we multiply this by 7, 7 minus 1 is 6 over 21 minus 1 over 5. So that is, mm, this can be divided by 3 further, 2 over 7 minus 1 over 5, and that can be written as 3 over 35. Now this is the answer that we have got by changing the order. I do not know whether it is the same as this. Let us try. We should try. Okay. Um, 1 over 50 minus 1 over 3. So that becomes 5, 1 minus 5, which is negative 4 over 15, and okay, and then this can be written as 30 minus 28 divided by 105. I think something has gone wrong, probably 2 over 105. Here our answer is different from this. Probably some computation mistake, but fine, never mind. You can check it for yourself. The answer should be same. If I find I mean, I happen to find the error in this, then I will clarify it in the next lecture. But for the time being, let's stop. That uh, completes the, not completes, but at least these two examples tell us uh, how to compute the integral over general regions. And also they have, this is the beginning of the discussion on the change of order of integration. We have practically discussed it, but we shall take a deeper dive in this topic of changing the order of integration in the next lecture. All right, see you in the next lecture.